I would like to start with a beautiful type of bonding, which is ionic bonding. So let's do this with this one here. The question is, magnesium reacts with the fluorine, forming a compound. So we have a lot of questions about these. So the first one is, we have to determine the type of bonding, and then we have to state the formula of this compound. Next, draw the diagram of bonding using a dot cross diagram, and then we describe the bonding in scientific words. And now, what is the type of bonding? As we know, magnesium is a metal because it has 2 electrons in its outer shell, alright, and fluorine is non-metal. How to determine whether the atom is a metal or non-metal? We have to know that the location of the element in the periodic table determines this. So if the element locates in group number 1, 2, or 3, it means this atom, or let's say this element, is a metal, and not to forget the transition elements. For the groups number 4, 5, 6, 7, and 8, these are non-metals. So magnesium is a metal, fluorine is non-metal. Reactions between them leads to form a ionic bonding. What about the formula of this compound? We have to do, let's say, before drawing anything, we have to determine the formula of this compound. Determining the formula of this compound helps me and tells me about the number of atoms involved in this bonding. So magnesium, as we told you before, it locates in group number 2, which means it has 2 electrons in its outer shell. When the atom has 2 electrons in its outer shell, to become stable, it loses them. Whereas the fluorine, it has only 7 electrons in the outer shell and needs only 1 electron to become stable, so it will gain it. So we draw magnesium, and then we put the number of electrons lost below. Same for fluorine, we put the number of electrons gained. By the way, the number of electrons gained, lost, or shared are called valency. And then we make a cross multiplication. Then we got magnesium fluoride, MgF2, which is the formula. As we know, the formula is MgF2, which means we have to draw 1 magnesium atom and 2 fluorine atoms when we draw the bonding. And now, how to draw the diagram of bonding? Okay, the formula is MgF2, and magnesium has 12 electrons, fluorine has 9 electrons. Okay, so let's start drawing the magnesium atom. The first shell's capacity is 2 electrons, and then we put 8 electrons in the second shell and 2 electrons in the outer shell. F2, which means we have to draw 2 fluorine atoms. The first shell's capacity is 2 electrons, as we see, and we have 7 electrons in the outer shell. So we draw another fluorine atom. The electronic distribution of magnesium will be 2, 8, 2. Fluorine will be 2, 7. So for magnesium atom to become stable, we lose these 2 electrons. For the fluorine, we will gain 1 electron, and this one will gain 1 electron. After transferring of electrons, magnesium atom becomes ion, fluorine atoms become ion. The charge of magnesium atom is +2, so we want you to know that when the atom carries a charge, it's called ion. So here magnesium ion has a charge of +2 as a result of losing 2 electrons. For the fluorine atom, they gained 1 electron of each fluorine atom, so the overall charge of this ionic compound is equal to 0. So here we have the electronic distribution of magnesium, the electronic distribution of fluorine atoms. And as we know, after transferring of electrons, magnesium ion and fluoride ions have the noble gas electronic distribution, which is stable. And now let's define the ionic bonding. Ionic bonding is electrostatic attraction between the positive and negative ions. And you should know that this attraction is very strong. That's why all of ionic compounds have high melting point and boiling point. You should know that all of ionic compounds are giant structures. We're talking about million of positive ions, million of negative ions. So these ions are attracted to each other, forming a lattice structure. So the lattice structure is a three-dimensional shape as a result of electrostatic force between positive ions and negative ions. So if you want to destroy a lattice, you need a lot of energy to destroy the bonding between them. So that's why, as we told you before, they have high melting and boiling points. In the world of chemistry, there are three main kinds or types of bonding. So we covered the ionic bonding, and now we will introduce you to the new type of bonding, which is covalent bonding. The definition of covalent bonding is it is a type of bonds that takes place between non-metal and non-metal atoms, and this happens by sharing pairs of electrons to reach the octet, which means stable outer shell and filled outer shells. So let's take a beautiful example about it. Let's take fluorine. Fluorine is an element that locates in group number 7, which means it has 7 electrons in its outer shell. Alright, that's really cool. So if you want to distribute the electrons as we see, the first shell capacity, as we know, it has 2 electrons and 7 electrons in the outer shell. Alright, before we start, is a fluorine atom stable? The answer is no, because the fluorine atom contains only 7 electrons in the outer shell and it needs only 1 electron to become stable. So how to make fluorine atom stable? Actually, there is no source of electrons to be gained by fluorine atom to become a stable outer shell, because we have another fluorine atom. I start drawing a fluorine atom, and as we told you that the number of electrons in the outer shell of a fluorine atom is equal to 7, and it's not stable. And how to become stable? We want to share a pair of electrons between the fluorine atoms. So as we see, we want to share electrons with another fluorine. So in the nature, you never find a fluorine atom as a singular atom. You find it as F2 or a molecule, because in the shape of molecule it's the most stable form of fluorine. So if you count the number around the fluorine in here, we say 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons around the fluorine in here, and the same thing, we have 8 electrons around the fluorine. So both of them have the stable outer shell, or let's say the noble gas distribution or configuration. The question is, oxygen exists as O2. So can we explain this in terms of bonding? Of course, yes. So the first thing we should know that electron has 8 electrons, which means 2 electrons in the first shell and 6 electrons in the outer shell. So let's start drawing the first oxygen atom. Here we have 6 electrons in the outer shell. Oxygen is not happy because it needs 2 electrons to become stable. So what to do in this case? Oxygen needs 2 electrons, so it will form 2 bonds. So it will share another oxygen. The same story. So we have another oxygen that has 6 electrons in its outer shell. So what will happen here? The first oxygen has 6 electrons and the second one has 6 too. So these 2 electrons will come to the sharing area, and another 2 electrons will come to the sharing area. As I told you, one bond consists of 2 electrons, but in this area we have 4 electrons, which means we have 2 bonds. Let's count the number of electrons around oxygen, starting from here. 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons around the first oxygen. What about the second oxygen? We have 1, 2, 3, 4, 5, 6, 7, 8. So these oxygen atoms are very happy and stable because their outer shells are filled with electrons, so they exist as O2 because O2 is a stable form than one oxygen. So the formula of oxygen would be O2, but when we draw the formula of oxygen 2, it looks like this. In here we have the double bond. We have 2 pairs of electrons, forming two bonds. So this is a stable. Nitrogen is a gas and it exists in the nature as nitrogen molecule. Okay, so let's say nitrogen has 7 electrons, which means the first shell will be 2 electrons and the second shell will be 5 electrons, which means it has 5 electrons in its outer shell. But if you want to count the number of electrons that needed to become a stable outer shell will be 3. So let's draw the first nitrogen atom. As we see, guys, we have 5 electrons. A nitrogen atom as a singular part is not happy because it has only 5. This atom needs 3 electrons to become stable, but so it will share 3 pairs of its electrons with other nitrogen. So it will share its pairs of electrons with nitrogen. So we have another nitrogen atom and it has 5 electrons. Put in your mind, nitrogen needs 3 electrons to become stable. It means we'll share 3 electrons. So the first nitrogen will contribute 3 electrons, alright, and the other nitrogen will contribute 3 electrons in this area. So after contributing of these 3 electrons from both nitrogens, we got 6 electrons in the area of sharing. So as we see, we have 3 pairs of shared electrons. And actually, this is the definition of covalent bonding, which is sharing electrons. Okay, as we told you that we have 6 electrons in the sharing area, which means we have 3 bonds. So here we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons around the first nitrogen. What about the other nitrogen? We have 1, 2, 3, 4, 5, 6, 7, 8. And here we have 8 electrons around the nitrogen atom. So when we want to write the formula, we write it like N2. But when we draw the formula, it looks like this. And here we have triple bonds. And these bonds are very strong. So nitrogen exists in the nature as diatomic molecule. It is a molecule diatomic. So it's a triple bond. 3 pairs of electrons were shared. And it is a stable molecule. Okay, and now we introduced you to the ionic bonds and covalent bonds. And now it's time to understand how to name covalent compounds. The first thing, the only difference between naming the covalent compounds and ionic compounds is the numbers. We don't care about the numbers in ionic compounds. So when we say like MgCl2, we say magnesium chloride, and we don't care about the 2 and the chlorine. But in the covalent compounds, we care about the numbers so much. But we don't use the English numbers like 1, 2, 3, 4, 5, 6. We use these numbers. When we say 1, it means mono. When we say 2, it means di. When we say 3, it means tri. 4, tetra. 5 penta, 6 hexa, 7 hepta, 8 octa, etc. So these are very important parts. So I would like to take a beautiful example about these here. When we say carbon and oxygen, the first thing we should know, are these covalent compounds? Yes, because if they're not covalent compounds, we want to call them according to the ionic bonds naming. But here we have CO, we have carbon monoxide, we have CO, carbon and oxygen are nonmetals, so this is covalent compound. According to the rule, we have carbon, we pronunciate it or we write it as it is, carbon, carbon. But here we have only one oxygen, so we put monoxide, okay? So we write the first simple like as it is, which is carbon. Here we have only one oxygen, we say monoxide, okay? The second one is carbon, 2 oxygens, like carbon dioxide. So here we have carbon, carbon, and we have 2 oxygens, we say dioxide. Okay, for sulfur, we have sulfur trioxide because here we have 1 sulfur atom and 3 oxygens. We say trioxide. And these are covalent compounds. CCl4. Carbon and chlorine are nonmetals, so this is covalent compound, so we call it carbon tetrachloride. In here we have sulfur with fluorine. Both of them are non-metal, it's covalent compound. So we write sulfur as it is, and we have hexafluoride. What about N2O4? We have two nitrogens, so we say dinitrogen tetroxide. So these are the rules of naming of covalent compounds. So let's introduce you to the properties of ionic compounds and covalent compounds. We would like to start with ionic compounds. All of ionic compounds are giant structures, which means a lot of bonds, a lot of ions, positive and negative ions are attracted to each other. So this attraction is very strong, the high melting. That's why the melting and boiling points are very high. So if you look at this one here, we have a strong electrostatic force between the positive and negative ions and the ionic bonding. So it needs a lot of energy to overcome the attraction, and this is an example of a lattice. We have a uniform shape in a lattice that consists of attraction of positive and negative ions. And now let's go to the covalent compounds. As we see here, we have a covalent compound between hydrogen chloride. We have the molecule of hydrogen chloride. Hydrogen chloride is bonded with covalent bond between hydrogen and chlorine, and this bond is very strong. By the way, this is a covalent bond. So guys, within the molecule, the covalent bond is very strong. But between the molecules themselves, like the molecule of hydrogen chloride and another molecule of hydrogen chloride, the bond here is weak, and it's called intermolecular force. Let's make a comparison between ionic compounds and covalent compounds according to the solubilities. So the first thing you should know that the ionic compounds are soluble in water because water molecules are able to separate the ionic compounds into their ions. But for covalent compounds, the water molecules are not able to separate them. And for sure we have some exceptions like HCl and sugar. What about the electrical conductivity? You have to notice that ionic compounds in solid state do not conduct electricity because the ions are packed in the lattice, so there are no free ions. That's why they never conduct electricity in solid state. But they conduct electricity in liquid forms. Liquid forms could be molten ionic compounds. We can melt them at high temperatures so the ions become free to move, so they can conduct electricity perfectly. And the other way is make an aqueous solution. Aqueous solution means you have to dissolve these ionic compounds inside water and then conduct them to electrical, or let's say a voltage, and they will conduct electricity perfectly. Covalent compounds do not conduct electricity because they don't have any ions. We told you before that all of ionic compounds are giant structures, but they're not the same as in covalent. Covalent compounds can be simple covalent compounds and can be giant covalent compounds. Let's introduce you to the properties of giant covalent compounds. One of the most important one is that they have high melting and boiling points. And if you want to explain this in terms of bonding, giant covalent compounds have high melting point and boiling point, and this is due to the strong covalent bonds that needs a lot of energy to break down the bonds. Allotropes are different forms of same element. I want to give you an example that appears like a giant structure, which is carbon. Carbon has two forms. The first one is graphite, and the second one is diamond. Both of the graphite and diamond are made of carbon. So let's start studying the graphite. Now, graphite has a lot of properties. For a graphite here, each carbon is bonded to 3 carbon atoms. So this is connected to this one, and this, and this. But we know that carbon locates in group number 4, which means it has 4 electrons in its outer shell. Here it has only 3 bonds, which means there is an electron that is not bonded. So this electron will transfer, or let's say will move across the layers. So that's why graphite is a good conductor of electricity, due to the delocalized electrons. Another feature for graphite, within the molecules in here, the bonds are very strong. But graphite is ordered as sheets. So here we have first layer, or let's say the first sheet, and the other sheet is down below. The bonds between sheets are very weak So these are the bonds. These bonds are very weak, so they can't slide over each other easily. That's why we use graphite as a lubricant, use it as a substance in pencil, so that we can write using that. So that's why you can write using pencil, because the sheets can slide over each other and then we can see the writing. The uses of graphite can be used as pencil, lubricant, and electrodes in electrolysis. For diamond, each carbon is bonded to 4 carbons, which means all of electrons in the outer shell are used in bonding to, so there is no free electrons in diamond, and that's why diamond never conduct electricity. So it doesn't conduct electricity, so diamond doesn't conduct electricity because, as we told you before, all of electrons were used in bonding, no mobile electrons or free electrons. Diamond is considered as the hardest substance on the Earth's surface, so we can use it for cutting and drilling metals in glass because of their hardness, and the other use is in jewelries. Metallic bonding is the bond that holds all of metal atoms together, and this has happened by, we know that electrons in the outer shell of metals start to move around between the atoms themselves, so attraction force generates between the free electrons and the positive metal ions, and that's why the metals are very hard and their melting points and boiling points are very hard with the strong bonding in them. Metallic bonding is attraction between the metal ions, which are these, and the free electrons. Free electrons are moving around everywhere, or let's say they have high melting points and boiling points, and this is due to this strong attraction between the metal ions and free delocalized electrons. And now let's go to the conducting of heat and conducting of electricity. When the heat is applied in metal, the particles start to move faster and vibrates in their positions. That's why they conduct heat. The conduction of electricity is due to the free electrons that move through the lattice, so that makes them conducting electricity. And now the other physical property of metals that are malleable and ductile. And here we have to describe and explain why metals are malleable or ductile. The answer is, when we apply force, the atoms can slide over each other without breaking the metallic bond, because we're talking about the free electrons that moves everywhere. So when this electron, for example, moves to this area, it creates a new attraction force, which is between this electron and this metal ions. And now, guys, I would like to tell you about the alloys. When we talk about alloys, it means we have a mixture of metals. These metals do not react with each other, they're just mixture. So we can prepare alloys by heating different metals and then mix them together. Why do we mix metals together? Because we want to enhance their physical properties to make them stronger and harder. The particles of metals in alloys cannot slide over each other, and this is due to the different sizes of atoms. Let's take an example of alloy, which is a brass. Brass is a mixture between copper and zinc. Why do we mix copper with zinc? Because it becomes erosion resistant, and it's used for, as we told you, for water taps and musical instruments. We have a lot of a lot of things like this. Okay guys, I hope you enjoyed this video. If you have any questions, you can ask me in the comments below. Have a nice day.